Hi there and welcome! I'll help guide you in your journey to start designing and making your very own robots. In the previous video, part 3, we took a look at the difference between analog and digital approaches. More specific, the components used. We saw the difference between active and passive components and the general buildup of a microcontroller. If you haven't seen part 1, 2 and 3, make sure to check it out. I've included links in the description below. In this video, we will take a look at an actual circuit. We'll create an analog approach as well as a digital one. Let's get started. We'll take a practical example of a circuit used in a simple obstacle detecting robot. As a sensor, we'll use an infrared distance sensor. It works by sending out infrared light with an LED. If an obstacle is in front of it, the light will reflect onto the object and into the infrared sensor. The sensor outputs an analog voltage. The closer the object, the higher the reflected light and the higher the voltage. The further away, the lower the voltage will be. That means a certain distance will correspond to a certain voltage. We can use this to signal the robot that it has to stop and possibly do another action to avoid the obstacle. In this example, we will light an LED as a visualization of our circuit working. First, let's see the analog approach. There are a number of ways to do this, but I will show you one of the simplest and most common ways. We will use an operational amplifier, also called op-amp. These are wonderful components and have so many applications in analog electronics. Here we will configure it as a comparator. All a comparator does is compare two voltages. If the positive input is higher than the negative, then it will switch the output to the positive supply voltage, in this case 5 volts. If it's smaller than the negative, it will switch to the negative supply voltage, which is 0 volt in this case. The great thing about op-amps is that they are extremely sensitive. Even the slightest voltage difference will make it switch. We connect the sensor output to the positive input. We do this because the voltage will rise when the distance gets shorter. We want to trigger something if the voltage reaches higher than a certain voltage. On the negative side, we will have to put a reference voltage, preferably something we can adjust to set the distance. This can be done extremely easy by using a potentiometer, also called variable resistor. When we connect it like this, we have created a variable voltage divider. It's nothing more than a resistor that we can adjust the middle point of. We use a 10 kilo ohm potentiometer. You can think of it as two resistors in series, R1 and R2. The value of those resistors change as we move the dial, but the total will always be the 10 kilo ohms. If we supply a voltage, the voltage will divide itself over the two resistors. The higher the value of the resistor, the higher the voltage over it. So, if the potentiometer is in the lowest position, then we can see the point is at ground level, or 0 volts. R1 is 10 kilo ohms, R2 is 0 ohms. This means all the voltage is over R1. So, since all the voltage is over R1, the voltage at the point above R2 will be 0 volts, because R2 is 0 ohms. If the potentiometer is in the highest position, the point is at supply voltage level, or 5 volts. R1 is 0 ohms, and R2 is the 10 kilo ohms. All the voltage is over R2, so R1 is 0. If, however, we set it exactly in the middle, the two resistor values are both 5 kilo ohms, while the total still remains 10 kilo ohms. That means the voltage will divide itself at 2.5 volts per resistor. So, the middle point level is set at 2.5 volts. This way, we can set the voltage anywhere between 5 volts and 0 volts by moving the dial between the upper and lower position. If we go back to our circuit, we have both our inputs of the op-amp connected. The only thing we still have to do is connect an LED to the output. We'll use a series resistor to limit the current for the LED. For a 5 volt supply, we'll use a 470 ohm resistor. And of course, connect the other side of the LED to ground to complete the circuit. And there, our circuit is done. Of course, the sensor and op-amp both still need power supply by 5 volt and ground, which I left out to keep things clear. As we can see, it works amazingly well. We can easily set the distance and the LED lights up accurately. For the digital approach, we'll use an Arduino, as this is the most common way. We'll connect the output of the sensor to an analog input of the Arduino. Yes, most microcontrollers have analog inputs. What will happen in short is this. The Arduino microcontroller will use an internally built-in ADC, or analog to digital converter. That's quite a complex piece of electronics that basically converts the analog voltage into a digital signal or binary code, as we saw in the previous video. It will send that code into the central processor. To set the distance, we'll use the same potentiometer and wire it the exact same way. Only this time, we'll wire it to the Arduino using another analog input. Now we will have two binary codes, one with the value of the sensor and one with the set level. We'll also connect our LED with a series resistor to one of the output pins, and of course the other side to ground. As always, don't forget to supply the Arduino and sensor of power as well. Now it's time to program. We'll write our code where we'll program the same thing as our analog circuit did. If the sensor value reaches above the set level, we will turn on the LED. Otherwise, the LED will remain off. With this simple program, the microcontroller will simply compare the two binary codes and turn one bit in the output block high, which is the pin our LED is connected to. As we can see, the result is identical to our analog circuit, even though the approach is quite different. This digital approach is simple, which is mainly thanks to the Arduino programming environment. Arduino makes it so easy and quick to program because all of the settings and communication with the microcontroller hardware are being done for you, behind the scenes. The developer of the Arduino environment have done that for you, so you don't have to mind or even understand the internal workings of the microcontroller, which is good and bad at the same time. Many people have argued about this. In my opinion, it's good to experiment with and build curiosity. Can you do many things with it? Yes, absolutely. Does it really teach you electronics? No, and that's a shame. Because Arduino has so many example code, you can just copy and replicate what other people did and create something quick, without really knowing what you just did. If you want to get creative and innovative and go beyond the classic Arduino projects, you better focus on learning electronics. There is a world beyond Arduino and even beyond microcontrollers. If you get to understand that world, your possibilities are endless. So, to conclude, the analog approach is a simple circuit which works pretty well. The digital circuit uses a different principle and is quite a bit more complicated. But thanks to the Arduino programming environment, we were able to get the same result in a simple way quickly. Join me next time for more to start building your own robots.
Stay tuned to learn more about how to start with making robots. Don't forget to subscribe and see you next time.